All right, welcome back. So now we're going to talk specifically about Young's double slit. So how does it work? Well, we have a light source. So I'm starting down on the light bulb here, and the light source produces waves in phase. Produces waves in phase. All right. So it is a source of light, is basically what that boils down to. And the light waves emanating from the light bulb are in phase with each other. They emanate out in all directions from a light bulb, from a source, and those light waves will strike the slits in a screen. So I'm literally talking about a screen that has two slits cut in it. Okay, just take a penknife and you just cut those slits into the cardboard or the paper. What happens if we put a screen behind it? What will happen is we end up with an alternating light and dark pattern. All right, and I'm going to show this with an applet in a little bit here. So we're going to have these bright regions of intense light. So bright regions. And then the alternating bands will be dark regions. So if we let light pass through those double slits, we end up with an alternating pattern of light and dark regions. So let's talk about the why on that. Then we're going to take a look at some of the math involved. So top view, looking from down on top of this, we're looking at our two slits, and the red lines represent the light rays. So the distance we're talking about between the two slits we're going to use as lowercase d. We are looking at, from this point source here, we have a light wave that reaches that distance. So we are going to designate that length from there to there as capital L subscript 1. So length number 1. From the other slit, we're going to work it backwards because I want it to meet at the same kind of in phase. It's going to look like that. And that distance we're going to designate as L2. Now, if we were to talk about what do you notice between the two light waves here, I'd ask, what properties, what do you know about the relationship between L2 and L1? And the majority of people would be able to tell me that based on my diagram here, L2 is greater than L1. So what we do then is if we subtract the two or find the difference, that L2 minus L1, we call that delta L, and that is our path difference. So how much further did light have to travel to reach the same point? Difference. Okay, so there's your L2 minus L1. So let's talk about that. We have two possibilities. We could have constructive interference. So that's when two crests meet. So constructive interference. So what would delta L have to equal if we were going to have constructive interference? Well, we want that delta L to be a multiple of a wavelength at that particular point. So if that distance is one wavelength off, two wavelengths off, then you will end up with constructive interference. All right, so for example, let's say I have that wave there, and the other wave is longer. I need to make sure it does one full revolution. I need to move that light wave down. I need it to start way back here so that these starting points here and here are identical in order to have constructive interference. So there is my delta L that I'm talking about. So the wavelength has to be an integer value off of 1. So M is an element of integers using your math notation. So how do we create destructive interference? So same diagram off to the side here. Delta L would equal. So I'm going to slide my red drawing over. And now I have crests and troughs matched up. And now all of a sudden, that delta L is equal to half a wavelength. All right. So how we write that up then, we have M, one wavelength plus another half wavelength So we offset it or perform a phase shift, and now we have it multiplied by lambda. Again, m has to be a multiple of integers. All right. So that's how we can we create constructive and destructive interference. We're playing with how long the waves are from there to there. There's got to be some additional part wave or full wave that creates those bright and dark regions, giving us the constructive and destructive interference. All right. So again, I've already done it on the previous page here. So you have your D1, your L1, L2, and I've already come up with that delta L is L2 minus L1. Now delta L has to be a positive value, so I'm going to put it in absolute value brackets. All right. Delta L has to be positive. If it turns out it is a negative, it just means that the diagram is shifted, and it would actually be, it would look like this. So if you accidentally did it and you got a negative number, it just means the situation's flipped, you're on the other side. So that's why we always assume it to be, or make it absolute value, because it's got to be positive. Just meant that L1 was longer than L2. And secondly, M must be an integer. All right, sorry, kind of went through the proof on that on the previous diagram. So I do have a page here with equations. We're going to come back and fill in the rest of the equations as we go through the math. So we already have our first one. L2 minus L1 is equal to m lambda. Corresponding one here, L2 minus L1 for destructive interference is that half phase shift. And that gives you your destructive. So we're going to come back to this slide in a second, fill in the rest of the equations. I want to do some of the math for you, just because you need to see where it was developed from and realize it's just playing with geometry, trigonometry, and so on and so forth. So similar diagram before. There's your L1 path. There's your L2. There's your D. And what we look at, if I talk about this angle right here, if I talk about that being theta, and I draw a perpendicular line between the two, what the resulting base value, so I'm talking about this part of the right angle triangle that's created, from there to there, we can call it x. And what is x? So x is the path difference. Okay, it's how much farther the wavelength has to go to kind of get to the same starting point as L1. So that's how much extra L2 has to travel before you get going. So that tells me that x is going to equal L2 minus L1. So what is the value of x then? Well, we can use our trigonometry skills from grade 10. And we are looking for, if we label it, our D is our hypotenuse, opposite, adjacent. We're end up using sine theta equals opposite over the hypotenuse. So sine theta equals x over D. I want to isolate for x. Excuse my voice, kind of losing it today. We end up with d sine theta. So that's what our x value is. So we can make that substitution then, and we come up with the formula that slit width multiplied by sine theta is going to equal L2 minus L1. We end up being able to add that to the previous page. All right. So we go back a slide then. Over here, L2 minus L1 is equal to d sine theta, which would mean that d sine theta, we're going to do all the iterations, is equal to m lambda as well. Similarly, L2 minus L1 equals, d sine theta. So those two formulas are identical on both sides, but the one that you're probably going to use more often is that half phase shift calculation right there. All right, now, since I have the diagram up, I'm going to talk a little bit more about some of the geometry when you're measuring or finding that angle theta. Okay, so I'm just going to play around with that diagram that exists already. So if I add in a center line here, and you don't necessarily have to do it with yours, so I'm going to add that center line in, that's black dashed line I just added. Maybe I can pick a better color. It's red. All right, it's our center line. It's right between the two axes. What it does is, maybe what I'll do, I'm going to maybe redraw that. And the reason I wanted to redraw it, again, you don't need, you give yourself a quick sketch, but in the end, it's not too crucial because this is just explaining why you took a certain measurement on the lab. All right, so if I take that, still draw that perpendicular in, it also creates another triangle right here, which is 90 degrees. This is way too small, so I'm going to expand that out a little bit, make it much, much bigger for me to draw. All right, one final time. So 90 degree, this is theta, which means that this angle in here is 90 minus theta from geometry, which means opposite angle theorem, that angle right here, two intersecting lines, will also be equal to 90 minus theta. All right, so those two angles are going to be equal. Just kind of draw that a little bit better for you. Which means that here we have another right angle, which means that that angle right there is going to be theta, which means opposite angle theorem. That angle's theta. And that's important because the lab I have you do, or the investigation I have you do, you're measuring that angle there. That's why the theta works. When you do the geometry, the theta translates from here to here to here. So we measure off the center line, and that is the reason we measure off that center line, is because geometrically it is our theta value. So note that that angle, and the thing you need to be careful with, because the next one I'm going to go to, that angle comes from using L2. So my theta comes from L2 and the center line crossing. The next one I'm going to talk about is the angle between the center line and a line drawn from that intersection with the screen. So this one right here. So if we call this the angle between center line, and you'll notice that I'm going to call this just length L, no subscript. So you got to be careful when you write out your formula sheet. And the far side, XM, that's going to be distance from center line okay, theta M is our central angle. And our L is just the length from center to the screen. So we're going to leave it as is. If we do some of the trigonometry here, we find that, again, if I use sine, just from SOHCAHTOA, so that's your opposite over hypotenuse again. This time I'm going to use sine theta M equals, my opposite length is XM, so the distance from center line to what we're looking at is a bright region here. So I'll just add that in up here. Distance from center line to bright region. Over the hypotenuse, which is L, the distance from the center of the slits to there. We can rearrange it or do a substitution, and I'm going to leave it because the next, I just want to show you where that comes from, and we'll finish it up in the next video.